Go.
Hello!
Hello, Mr. Eric, Mr. Ryan. Hello, how are you today? Good. Okay, so remember yesterday we talked about dynamic programming. Yeah, we have been talking about dynamic programming for a few days, and yesterday we talked about using dynamic programming to climb the stairs. Alright?
Yeah.
Okay, so now today another interesting problem. Okay, so suppose there's a street. Yeah, a street.
And we're in a car.
No, and there's a house. House 1, house 2.
How small? How house it could be on the street? The cars would just smash into it.
Yeah, that's okay. Wait.
They
Okay,
could
so
be
look.
on the path.
The
They
path.
have to have doors.
Okay, that's fine. That's fine. So suppose there are
houses.
6 houses, and for each house there are some money in there. Okay, you know, some goods. Yeah, and we use the number integer, for example, to represent how much money it has. Yeah, like for example 5, 3, 2, 1, 10, 6. Okay.
What?
So-
Pounds?
Yeah, pounds. Yes. And suppose.
But that's not a lot.
Suppose a robber, you know the robber?
Yeah.
Robber, which is a bad guy, yeah?
Yeah.
Robber, yeah?
Yeah.
And one night, very quiet night, he or she, decides to rob those values, the goods in this street, in the house on this street, yeah?
Yeah.
But the thing is that if he rob this house, he take this money, yeah?
Yeah.
And if he or she take this money, then the police will be notified because if there are two neighboring house, yeah.
Mm.
If you take the goods from 2 neighboring house, the alarm will fire off, yeah, will be off, yeah.
Yeah.
And then a police will come. So you shouldn't take the goods from the 2 neighborings. Okay, but you can take.
I've never done that because I don't have the key.
Yeah, that's okay.
Yeah.
But that's why the robber broke into the houses. Okay, so the thing is that look, the robber could take at least 5. But
I'm not strong enough.
look, you could take 5, yeah, and then 2, yeah,
Yeah.
and then 10. So how much together? So basically you want to pick the values, the numbers, yeah, numbers. But not picking the neighboring. So if you pick 5, you shouldn't pick 7. But if you pick 5, you can pick 2 or not pick 2, pick 1. Yeah. So this is 17. Can we have a better one? Look, we can pick 7. Yeah.
You can pick
6, 7 and 1, and 6. 7 plus 10 plus 6, which
14.
is what?
Oh wait.
33. Yeah, so this is obviously
33.
better. Oh, no. 7 plus 1 plus 6. Plus 1 plus 6. So that's how many?
14.
Okay, 14. So it's not better.
I
Okay.
told you.
Yeah, okay, my mistake. Okay. And how about, are there any better ones?
I don't. Wait.
I think this is the optimum one. Yeah, this is the optimum. Yeah? Okay. How about 7 and 10? 7 and 10. But again, the another solution will be 7 and 10, which is 7. But that's okay, you can skip 2. Okay, so any ideas? How are we doing this? Any ideas? Any thoughts? Using the dynamic programming, since we are on this subject.
Use the biggest one.
Biggest one?
The biggest one.
What biggest one?
10.
You pick the biggest one, and then?
The second biggest, but if it's
But
next
the
door
second biggest
neighbour-
could be the neighbor.
Yeah, then you do this.
Third
biggest.
Third biggest, and then, so your strategy is how do you pick it?
Have to pick it up.
So for this,
Pick it up.
for this is
Have to pick it up.
yeah. How do you pick it?
Have to pick it up.
Yeah. What's your strategy? What's your strategy to pick it? You pick the largest one,
Yeah.
and then you start from the largest one, and then to pick to jump at. You want to pick these two or not? Or you can pick 5, yeah. Or you can pick. Suppose, look, if this is 8, right? If this is 8, so you 10, and you pick the second and the largest, which is 18, yeah?
Yeah.
And how about if I have this another 10 here? Maybe I put this 15 here.
Then 15, 10.
So you always pick the second largest. And if this is 19 here.
I'll pick 19, 15, then I'll pick 6.
19, 15, 6. Okay, so your strategy might work, but there are some cases it might not work. Okay, and I need to come up with some. So you always pick the largest one, yeah. You always pick the largest one. So let's say 18 here, largest one, and then you pick, and then I pick.
My strategy. So I mean.
You pick 19, yeah.
Yeah.
And then.
Pick a 19. What's that?
Sorry.
What's this?
No, I'm thinking of I'm
20.
thinking of, okay, maybe 20 here. So you pick 20 and 19. Yes?
Then 6.
And a 6. It might work, yeah? It might work. 20, you pick a 20. How about that? It's 19 here as well. Okay? And then you pick 19.
You can pick 18 as well.
No, once you pick 19, you can pick 18 because they are neighbors.
Well, how about if you pick? Oh yeah, no.
Yeah.
So it doesn't mean that you can pick 19 and 6.
You can pick 19 and 6. Yeah. Okay, so I'm trying to think about the negative examples.
19 and 6.
Yes.
What's negative?
I mean the one that your strategy doesn't work. So look. So I'm thinking of you always pick the biggest one. Yeah, a biggest one. And how about if they are duplicate numbers? So which one you pick? Yeah. So
there's 3 of them.
Yeah, I know. So which one is largest? There's no largest. Well,
there's 20.
Okay. Maybe that look 19 here. So what do you pick?
I'll pick definitely one of the 19s.
Yeah, but now you then need to proof of search, right?
Yeah.
For example, all are 19. So what happened?
Wait. That only 3 19s.
Can you pick 4? Yeah, you can only pick 3. So that's how many numbers? 2,
Maximum
4, 6.
3.
Yeah, because every other one, yeah.
Yeah.
So every other one. Okay, so it seems that if in this case you just pick every other one. So do you come up with some general approach to approach that?
Oh wait.
Yeah, you can also search from here. You can search from this side. You pick this one or not pick this one. Yeah. Once you pick this one, you're not picking this one, and you go to the next. Yeah. Yeah. So you start from the search. Depth first search. We can do a depth first search, right? Yeah. Alright. Do you remember that depth first search, DFS, or BFS also work as well. So basically the tree. I start from the first house. First house, right? I pick. This one is pick. Yeah? And then this one is not pick. I'm constructing the tree, but you can search it with depth first search or breadth first search, right?
Yeah.
It doesn't matter. When I pick the one, and the next one I will pick number 3. But I cannot pick number 2, right? I pick number 3, yeah? Yes?
Yeah.
Pick 1.
Then
Pick 3.
Number 5.
Pick 3. Yeah? Pick 1. Not pick 1. Not pick 1. And then I what should I do with the not pick 1?
Not pick. Don't pick 2.
Yes, but so maybe we can refine this tree to just like if I have one and I pick one, okay? Pick one, so the next one will be 3, yeah?
Yeah. Or you can
Or
you can do
5, or
can you do 1, 4, and 6?
yeah, as long as it. So as you can see, when I pick one, I can travel to. When I pick one, I can travel to 3. Yeah, pick 1 to 3. And when I start from 3, I can start from 5. Okay, all right.
Yeah.
So, but for this one, so look, because it has lots of possibilities. Pick 1, and then I can pick 3. I can also pick 4 here, right? Yeah. Yeah, and I also can pick 5, pick 6, you see, this is very complex, alright?
There's no 7.
I know, I'm just giving an example. So do you get it? So look, this is very time consuming because for each node, the next node, you could be any from, if you pick the node I, so the next node, when you are I node, yeah? So the next node could be from I plus 2 to n, right? Yeah? Alright?
Yeah.
So what's the complexity of this one? So there are duplication here. Oh, it's very exponential, you know, it's exponential. N
something.
For how many nodes are there? There are n nodes, yeah? Roughly n to the power of n. Yeah? Yeah? So look, actually this is a bit complex. Look, if you pick this, yeah?
Yeah. You can pick.
Pick this.
Yeah.
Or pick this, yeah? If you pick this, look, if I pick this one, and pick this one only, this is not optimum, yeah? Because I can also pick this one. Why not pick it? Alright?
Yeah.
So look, the tree has duplication. So somehow we are searching some branch which is not optimal. We know, right? Because look, if I pick this one, and the next one I skip 3 and I pick this one, this is not optimal because I know I can always pick this middle one, which is more value. Am I right? Yeah. If these values are all positive, do you get it? Yeah. Okay, so this is not optimal. So the DFS or BFS may work if the number of the houses are small, maybe like 5 houses, 10 houses, the computer is fast, yeah? If 5 houses, 5 to the power of 5, it's very small number, yeah? Look, but if it's 100 to the power of 100, this is a huge number, yeah? Yeah, am I right? 100, there will be 100 zero after 100, yeah? Maybe how many zeros? I don't know. 200 zeros, yeah? Yeah? Okay? So that's a huge number. The computer wouldn't be able to compute it, you know, for in a short amount of time. Okay, so this search, brute force search, we call it brute force search, is not ideal. So I give you a hint, the dynamic programming. So suppose I'm here and in the last house, yeah?
Yeah.
So does it, if I'm at this last house, and then I can collect it, yeah? If I collect it, I can't collect this one, yeah? I can't pick this one. So I will compare to, if I pick this one, if I pick this house, I will pick the previous location will be this one, right? Yeah? Or I don't pick this one. And the previous location could be this one. Do you see it? Yes?
Yeah.
So look, if I use Fn to represent the number of values I can collect, the numbers I can collect at house n. Yeah? Am I right?
Yeah.
So let's see, F1 equals what? If I walk from the left to the right, okay? So F1 is representing the number of values that I can collect from house 1 to house n, you know, between this range. F1 equals what?
F1 equals
the house 1, yeah?
Yeah.
Because look, if there's only one house, then I can pick it. I either pick it, yeah?
Yeah.
Yeah, because if I don't pick it, I got nothing. I pick it. Yeah?
Yeah.
So that will be house 1, okay? Okay? F2 equals what? So there are 2 houses. So
Pick one, the biggest.
yes, we'll pick it. So that will be max of house 1 and house 2, right? Yeah?
Yeah.
Yeah, because there are 2 houses, I can pick 1 or 2, it doesn't matter. So look, if Fn houses, so how should we write it? Okay, I look, UB Fn. So if I pick it, what's the value? If I pick it, and house n. So if I pick it, what's the value? F. Pick it, that will be house n, right? House n, yeah. I pick it, yeah.
Yeah.
N plus which value? Plus which value? This bit.
Yeah.
What's this bit?
So
I pick the house n, and I can't pick this house n minus 1, but I can check those values. So this is the subproblem of which what? F what? Look, Fn. I pick this one, I can't pick this one, so what's this bit, this problem? Fn and what?
n minus 2?
Yeah, well done, be confident, look. Yeah, got it? So I pick this house, n, I can't pick this n minus 1, but I can pick this bit, yeah, which is the problem of n minus 2, yeah?
Yeah.
And maximum of this, if I don't pick this one, so what's the value? If I'm not picking this one, and what's this bit? If I don't pick this one, then I could possibly pick this one. And what's this problem? What's this problem? What's this?
N minus 1?
Well done! Got it?
Yeah!
So do you see? Fn, the house n, there are 2 choices. I pick it, then the problem will be the house n plus Fn minus 2. Yeah? I don't know what happened here, but I know this is the problem, the answer for n minus 2. Yeah?
Yeah.
Or if I don't pick it, then the problem is Fn minus 1. Yeah? Because I don't care what happened here, but if I don't pick this one, then the maximum value I can get is from this bit. Yeah? What's this? Dynamic programming equation. So we can just solve it. We think this. Look, this is the terminal condition, F1, F2. You know how to solve the base condition, the smallest problem, F1, F2, right?
Yeah.
And then now we have n. And the Fn can be divided into a smaller problem. Yeah, you see? Look, in order to calculate Fn, we want to calculate Fn minus 2 and Fn minus 1. So this seems look similar to a Fibonacci number. Yeah?
Yeah.
Except that this slightly different. We need to add the value. The value of the house are known. Yeah? Got it?
Yeah.
Does it make sense?
Yeah.
What's the complexity? If we're using the notebook thing, yeah? Do you get it? We are talking about the notebook minimization. What's the complexity? Oh, yeah, O-N. Because they are, why is O-N?
We're using a notebook.
And then for each house, Fn is only calculated how many times? How many times? We're using the notebook. Why are we using the notebook? We are going to remember it, yeah?
Yeah.
So for each house, there's only calculate how many times?
Once.
Yes, that's why we're using notebook. Okay, let's write this. So it's simple. Got it?
You want it in 15 seconds?
Okay, I'm going to write it, okay? Look, define, let's say f function, and then we have the house value, okay? House value, yeah? House value. And then, okay, let's maybe just do the value, okay? Value array. value. Comma, okay? So the length, n, will be length, am I right? Yeah? Yeah, the length. How many houses? Okay? This is a list of numbers, yeah? V will be like 1, 2, 3, 0, 5, 7, yeah? It will be like that, yeah? Okay? And then n, length n will be 1, 2, 3, 4, 5. So what's n here? What's the value of n? What's the value of n? N equals length v. What's the value of n?
Length.
How many elements there?
5.
So what's n?
5.
Yeah, it's easy. Okay, now we need to create an array. Okay, let's say dynamic programming array. Okay, dynamic programming array equals 0. Initially, for each value is 0. Look at this syntax. Bracket 0, but times, we use the star, yeah? Times n. So what it means is that n is 5. And after this, we're creating an array of 5. So which will be 0, 0, 0, 0, 0. Got it?
Yeah.
So after this, dp is this, yeah? Yeah? Is this simple? Yeah? Times n, yeah? A bracket, a bucket with number 0 times 5 equals this. Got it?
Yeah.
Okay. Okay, now, look, if n equals 0, okay, we return 0, okay? If there is no houses, we return 0, okay? Yes? Actually, this should go here, okay? It doesn't matter. If n equals 1, what should we return? If there's only one houses, what should we return? So?
Pick it.
Pick it, so which is V0, yeah? Yeah, V0 is the first house, yeah?
Yeah.
If n equals 2,
The biggest one.
return, so how do we write it? Return max V0 and V what?
1.
1. Okay, now this is, okay, then work. Return, yeah, the thing. I want to pick the maximum of what? Of these two. If I pick the actually we are missing a parameter here. We are missing a parameter. Actually I want to pick k. Okay, now it's k. So look, this will be because it's not n. So n is how can we write this better? So look, if n equals so actually this value should be put it outside. Okay. So look, if n if k equals 0, k equals 0, return 0. If k equals 1, return v1. If k equals 2, return v2. Return, okay, I'll fix it later, okay? Return maximum, if I want to pick k, I'm currently at k, so the house value will be vk plus f v k minus 2, right? Or, if I don't pick it, so it will be f v k minus 1, right? Yeah? Yes?
Yeah.
Come on, yeah. Okay, so now, so we can call this as fv, then length v minus 1, because we are getting that. So we don't need that dp value, yeah, because look, it will be going, it will be, there's base condition here, yeah? So what's missing here? If I implement this, what's the complexity? Come on, what's the complexity? Because this is recursion, we don't need to let dp array, but I'll show you later why we need it in the top bottom up dynamic programming. This is top down, remember? Top down. Because in order to calculate fn, we need to calculate fn minus 1 and fn minus 2, yeah? And this is the equation, yeah? Okay? What's missing? What's missing here? We need to cache it using the
LRU.
cache, yeah? Caching. Okay, look.
What's the A in a circle?
Add. Actually, you can just do cache. Yeah. This cache thing is equals to add ARU cache. None. Okay, this is the same thing. These two. This is short cache. Or we can do this using the notebook. Yeah, remember? Yeah, yeah, notebook. Right? Yes. Notebook, and if notebook equal if k in actually if we move this v outside, yeah, we don't need to pass v is not changing. V is known, right? Array. The house value is known, so we k. This is just fk. Yeah, got it? So if this value is outside, if you want to reference it, we need to use the global keyword. Global v. Okay. So look, using the notebook, and then we can do this. If k in notebook, we return notebook k, and then before returning the value, we save this into a value, and then notebook k equals value, return value. Alright? I'm going to write it. It's quite similar than yesterday. Okay, so I'm talking about the. Okay, look. I talk a little bit about Python here. Look, Eric. Define, this is a function f, yeah, with nothing. And if I want to print Eric here, yeah, Eric here.
Yeah.
Eric is defined outside this function. Eric equals 8, okay?
Yeah.
Yeah. And
I'm not
this
confusing number.
look, yeah, okay. Look, this is not going to work. Why is that? Because this function is in the scope. In the scope, different than this. But in order to use Eric here, I need to add a keyword, global Eric. That means I want to use Eric and then print Eric. Eric will be 8. If I don't add this, this will print. This will be unreferenced. It will be none. Okay, because this Eric only lives here. Yeah, it doesn't live outside. And then if you want to use outside, you have to tell computer, okay, I want to use the Eric from outside, which I need to add a global. It's in the global scope. Okay? Yeah, got it? Okay, this is one thing.
How does he know I'm 8?
Because you're assigning here Eric equals 8. And you can also do this. Look, define f. You can put a value here, n. Yeah, look, come on, and then you can print Eric. Okay, if I do this, look, Eric, yeah. Now that's okay because this Eric is this Eric, and then in order to call this, you have to call this f Eric, yeah, right? And then you will take this Eric value, pass it into the function, then you print Eric, which is 8. Do you get it? Yeah. Okay, this is passing these parameters. Okay, so previously that was top down, yeah, top down dynamic programming. If we want to calculate fn, we calculate fn minus 1, fn minus 1, and the other way of calculating it, which is called what? The other direction of dynamic
Bottom up.
Bottom up, yeah, well done. So in order to do it, the houses, yeah, I can just start here, and then I can calculate from the left to the right, from the f1, f2 to fn, right? Yes? Yeah? Okay. So that one will be without the recursion, yeah? Okay, so let's do this. Define f, and we have the houses, and we have the houses, okay? So now, again, we need to do this length equal v, yeah? Okay, and then now dp, this is the value of dp. dp equals 0 times n, so we have an array to keep those values. Alright? Yeah, to keep those values. And then, again, I'm not going to write it. If n equals 1, okay, let's write it. If n equals 1, return what? v0, yeah? Yeah? This should be put in the before that. If n equals 0, what should we return? Return what? 0. If n equals 2, return what?
Return max.
What? V0 and then V what?
1.
Yeah. Okay, now this is interesting. And then we can loop it, yeah? For I in range. Start from what? Start from what?
V0.
Starts from number 2, V2, start from 2, yeah? 2 and then n. Look, we just return it, yeah, but actually we also need to do this. If n and here I need to do this dp0 equals v0 and dp1 equals max v0 v1, right? Yeah. So that array, remember this dp array, yeah? Beginning with the values. I need to update the first 2 values, yeah? This first value will be v0, yeah? Because if I pick the first house, I can only pick one, yeah? The second value will be max of v0 and v1, right? Yeah? And then start from 2. Look, this is the magic. dpi equals max. Can you say it? It's almost finished. dpi equals max what?
V.
vi plus what?
V.
Sorry? I pick this house, and what's the value I need to get?
I.
Vi plus dp what? I pick the house, and then dp, what's the smaller problem I need to add? Remember, I pick this house, and then I need to, it's the total value I can have up to this point is this house, picking this house, and the previous what? I what?
I.
Minus what?
1.
Why is 1? I pick this house, I can't pick previous one.
2.
2, yes. And then, or I don't pick this house, and but which is dp what? And then I can
dpi.
I what?
1.
Yeah, okay. So let now return which value? Return this is the dp array. I calculated along the way which value I can return. dp what? The last value, yeah?
Yeah.
Because the n house the last value will be the maximum value I can get for this n house. So dp what? The last value. What should I put here?
dp.
What's the last value? The first value is
minus 1.
well done. Yes. Good job. Yes. So look. This is bottom up dynamic programming. We fill in this array. Remember the Fibonacci number, yeah? 0, 1, 2, and we start from 0, fill in that way. The previous recursion with the notebook thing is the top down, starting from the last one and going backward. This is starting from the beginning, going forward. And then we use an array dp equals 0 times n. Yeah, this is checking, and we fill in the first 2 values. dp0 equals the first house, yes?
Yeah.
Because we can pick it. Yeah, it's better we pick it. If we don't pick it, we get nothing. The first one, the dp1, for the first 2 houses, we just pick the maximum one, yeah?
Yeah.
And then we're going through the third house. Yeah, because in computer it starts from 0. The 2 is the third house. And dpi equals, if I pick this house, then I can also collect the maximum previous I minus 2 house. This is the sub problem. Or if I don't pick this house, I can pick the previous I minus 1 houses, right? Yeah?
Yeah.
And then I return the last value, which is the maximum value I can collect for the visiting the n houses. Got it? So any questions? Any questions so far?
No.
Okay. See you tomorrow.
No.
Say see you tomorrow. Bye bye.